Hi friends, let's have a look at problem 332, Reconstruct Itinerary. In this video, we're going to explain a solution based on post-order DFS. So here the problem nature is actually find the Euler walk in a graph. So if you are interested in some of the concepts in graph theory, especially the Euler walk or Hamiltonian walk, so here you can look at this post, or there's a book or reference in this post you can refer to. So here in this problem, so we want to find an itinerary, so which starts from GFK, right? And then the main assumption is that the itinerary must begin with GFK, and if there are multiple valid ones, we should return the itinerary that has the smallest lexical order when read as a string. So here, this order is also very important, right? In other words, so we need to have some constraint on the Euler walk. So here are some examples. So in the first example, it's actually very special. So actually, there is a property. So basically, so for this one, there's the out degree is 1. So here the in degree is 1, out degree is 0. So for this one, we have to start from GFK and go to MUC and LHR, then SFO, then SGC, right? So in the second example, so actually we start from GFK. Then due to the order, we need to first visit ATL, right? So if you look at the output, so from GFK, you visit ATL, and then you come back to GFK, right? And then you go to SFO, San Francisco, and then you go to ATL, then go back to San Francisco. So in short, so the main goal for this problem is to find the Euler walk. So a Euler walk in a graph is a walk that uses every edge exactly once, right? So so we are going to explain two methods. So essentially the same method, but with different implementation details. So one is in iterative format, so in which we are going to use a stack. So this is the so-called Hierholzer's algorithm. So, and another one is our recursion format, right? So both of the two methods are post-order DFS solutions. So the time complexity is big O of V plus E. So this V is the number of vertices in the graph we are going to build, and the E is the number of edges. So another ingredient for the solution is that in order to take the order into consideration here, right? So we are going to use a min heap. So with that said, we are ready to look at code. And in between, we are going to explain the main logic. Actually, the code is very short. So we are going to make it in different sections. So first is to build the graph. So here in the graph, in which we are going to use a min heap as the default container, right? So here we can do like this. So graph is collections default dict. So we are going to put a list here. So we are going to use this list as a heap, right? So this is the what we want to mention. And also this problem is very simple. It's in a simpler format, in the sense that we are given the starting point of the Euler path, that is GFK. So if you look at problem 2097, so you need to actually first find a valid start vertex, right? That's one difference of this problem here with problem 2097. So before we move further, I want to make a comment on these two problems. That is the current problem 332 and the problem 2097. So the two problems actually can be solved using almost identical code. After this video, you can try this problem, right? So then we are going to build, so this is the basically 1 or 2 lines of code for start and end in tickets, right? So what we are going to do, we are going to do heap push. So we're going to push to this graph S. So this is the list. We use it as a min heap. So we are going to push E, right? So here the order is produced by the lexical order because the E is a string, right? So that's it for this part. And then we are going to use the Hierholzer's algorithm. So the algorithm, so here what we are going to write is an iterative format. So we initialize a result. So this result is going to store a reversed itinerary in the sense of this problem. So here the thing is that when we look at a node, we want to first visit all the unvisited edges of that node, and then we are going to mark the current node or that node as visited. So we are going to do while stack. So we need to initialize the stack. So the stack will initially have this one, GFK, right? So this is from the problem assumption. So while stack, so basically what we want to do, we want to check if there are still edges for this node. You can think of GFK. So it's not visited yet. So next vertex. So it's so vertex, the neighbors for stack top element, that's a -1, right? So here we want to visit this one. We are going to heap pop. We pop from the current heap, min heap. So here actually we need to val this guy. So this condition means that for this top element in the stack, we still have edges not visited yet. So this is the edge connecting this stack -1, and the next vertex is the edge we are going to visit, right? Then what we are going to do is we are going to add this one to the stack. So next vertex, right? So after this while loop, so we actually finished all the traversals. Then we are going to add the current top node and stack into the stack, that is into the result. The result append stack pop. So this part is nothing but Hierholzer's algorithm. But the algorithm currently what we get for this result variable is a reversed itinerary. So we need to reverse this one. So here we can do in place. So after we reverse, actually we can return in the result. So this actually is a full solution to this problem. So you can see that this problem is marked hard. Actually, if you know the very method to solve such problems, the code actually is very succinct. So before we move to the second version, let's do a test. Yeah, it passes one example. Now let's look at the generic case. Yeah, it passes all the cases. So here actually you can have a feeling that here we effectively use the min heap data structure, right? So with that done, let's look at the second method, or second variant, the second version. So essentially the same method. So here I'm going to maintain this part. So build this graph. So next I want to write a hyperfunction. So this hyperfunction is essentially a post-order and DFS traversal. So we are going to use this result to hold the reverse itinerary. So here I'm going to define a visit or hyperfunction. Anyway, you can. So for a vertex, right? So our start will be, we are going to call this. Let me first write the structure of the code. So we are going to call visit GFK, right? And then we are going to reverse the result. And then we are going to return the result. This is our full code. Actually, it's almost identical to the first version, But here, let's write a recursive format. So first, let's mimic this one. So corresponding to this while loop, while graph vertex. In other words, for this vertex, we still have unvisited edge. So this next vertex, so will be hip pop. So graph vertex, right? So this is the edge we are going to consider. That is the edge starting from vertex and pointing to next vertex. So we are going to visit this one, right? Next vertex. So if we have visited all the vertices, so what we are going to do is we're going to append the current vertex to the result. So you can think of this visit as a worker which modifies the result. So, and that's actually it. So from the function call, so here, this is the visit, this is self call. Then after this self call in the while loop, we add the result, append the current vertex to the result. You can see this is a post order DFS traversal, right? So then we just call this function and then reverse this result and then return it. So let's do a test. Yeah, it passes the first example. Now let's look at generic case. Yeah, it passes all the cases. I guess that's basically about it for the second version. So overall, the time complexity for these two solutions is O of V plus E, right? So as a iteration. So if you are interested in some concepts related to graph theory, so for this problem, the Euler walk and Hamiltonian walk, you can look at this post. So with that said, I guess that's about it for the current problem. Thank you.